I'm Hiroshi Jinnai from Tohoku University, and as the chair says, the topic is very different. Okay, microscope, especially electron microscope. To begin with, I had a question from few people that where the Tohoku University is, so I just tell you where this is. This is a Japanese island, Honshu, and then Hokkaido. Professor Jinping Gong is here, somewhere here in Sapporo. Okay, this is Tokyo, Kyoto, yeah, as you probably know. Sendai, that's the place where the Tohoku University is at. And then this is about 300 kilometers north. And then it takes about an hour and a half by Shinkansen. So it's not that far. Some pictures from our campus. We can enjoy cherry blossoms in spring. We can enjoy, actually it's not enjoyable, but it's snow and summer. So it's not very hot in Sendai, but it's relatively cold in the winter. But we have only a few times a snow a year. And this is often asked, about 10 years ago, we have a big earthquake. And you know that tsunami hit the place. This is the Sendai was hit actually by tsunami, and many people, 20,000 people missing. And this is the place where we have a nuclear plant meltdown. So it was close. I was at this time I was not here. I was here. So that was okay for me, but for them it was not okay. All right, so that's just a small introduction of my university, and then our laboratory's objective is here. So I hear many stories about rheology, and that's a mechanical property. There will be electrical property, diffusive property, and other properties, right, of the material, especially polymers. And then we would like to understand this property from the structure. So to understand correlation between these two, we would like to precisely characterize the structures. When I say structures, I don't say the solution structure. I say melt structure, particularly phase-separated structure or nanocomposite. So in my talk, I will talk about phase-separated structure, polymer or nanocomposite. That's the topics. No solution structure. Okay. Anyway, so that's our objective. And then this is outline on my talk. I will start from the basic of the electron microscope, microscope in general, and then I gradually go into the electron microscope. Okay. And then for the topic one, I would like to introduce electron tomography. It's called three-dimensional TM, right? And normally, as you know, the transmission electron microscope takes the two-dimensional picture, but you can take a three-dimensional structure by electron microscope too. So starting from the introduction of the electron tomography, and then I talk a little bit about the principle of the 3D TEM. We sometimes call transmission electron microtomography, TMT, but in general, people call it 3D TEM. Okay, and then there's a problem associated with this electron 3D TEM. So there's one problem. This is how to solve this problem. So up to here, it's purely instrumental or methodological, and then I try to cover up to here in this lecture. And then in the second lecture, the day after tomorrow, I want to talk about these applications using all those techniques for the structural characterization. That's my plan, okay? So today, I'm going to talk about instrument. I'm going to talk about methodology. So I hope, you guys are not get bored too much. So to give you a general idea of which instrument is to characterize what size of the structure, that's here, okay? And I think last week you heard about scattering, I guess, right? So this is scattering, and this is microscope. And there's many different types of scattering and microscope. For the scattering, you know, as you learn, small angle X-ray scattering, so small angle wide angle X-ray scattering, and you know, light scattering here. So light scattering uses laser, whose wavelength is larger than the X-ray. So this is to detect the larger structure. Whereas here, neutron or X-ray, their wavelength is smaller, shorter. That's good for the smaller structure characterization. Okay, those are the other scattering technique. And then, as I think, as you probably heard, that the scattering technique is very good to characterize or to extract the statistical parameters like correlation lengths and other things, right? But in order to extract all those structural parameters, you sometimes need a model to fit the scattering curves. That's the thing. Okay. For the microscope, on the other hand, you like to zoom in and then try to look at the structure as you want. So it's a local structure characterization. This is more statistical characterization. Okay, among this microscopy, there are many things. Optical microscope, and this is one of the optical microscope, three-dimensional imaging technique, laser scanning confocal microscope, and there's X-ray CT, and SEM is one of the electron microscope, and TM. That's the topic I would like to cover this in this talk, and the AFM. So it's the same thing. The optical microscope uses a light or laser, so it's the same thing. The wavelength is larger, so the object you would like to see is rather large ones, like micron size. Okay, whereas TM using electrons, which has a very short wavelength, so it's good for the very short, very small object. X-ray, you know, this, like I say, this has a very short wavelength too. So you might wonder why this X-ray goes like this. Don't cover the nanometer scale. That's because X-ray don't have a charge, whereas electron has a charge. So for the electron, you have a magnetic lens. Then you can bend the ray. But for the X-ray, there's no lens available until recently. Okay, so that's why even though X-ray uses X-ray CT or X-ray microscope uses the X-ray as a source, the resolution limit is somewhere here. Okay. So is there any differences between the TM or the optical microscope? On your left, that's the optics of the optical microscope. On your right, this is a electron microscope. So on the top, we have a gun. That's the source of the electrons. And for the light microscope, you have a lamp or laser. And then you have a lens, and then you have a parallel beam to the sample, and then after that you have a couple of lenses to magnify the structures, right? So that's for the electrons, and then it's the same thing, essentially the same thing for the optical microscope. So the optical rules that applies to the optical microscope is more, in the most cases, true for the electron microscope and vice versa. So the thing I would like to say is that basically the microscope, either electron microscope or optical microscope, is the same thing. A little bit of a history of the electron microscope. It's been invented by a professor, Ernst Ruska, in 1931. And this is his first electron microscope. This is exhibited in Germany, Munich, and this is his note. back in 1931. And then he got the Nobel Prize of Physics in 1986, so 50 years after the invention of this microscope. Okay, so this is his young days, and this is when he got the Nobel Prize. Okay. And talking about the Nobel Prize, there's another thing, another one in the electron microscope community. We got that one, 2017 Nobel Prize, but in this case in chemistry. That's a cryo microscope, Cryo TM. You probably heard of it. And the reason is that the developing cryoelectron microscopy for the high resolution structure determination of biomolecules in solution. So it's protein. Okay, they quench the sample from the solution of the protein. They quench the sample. They actually put rapidly put the solutions, small amount of solutions into the liquid ethane, so that the water doesn't crystallize. So it stays in the amorphous phase. So if it's crystallized, then you cannot get the image. So that's a rapid quenching technique, and then after that they transfer the frozen sample into the cryo microscope, in which the sample cell is also cryogenic cooled at the cryogenic temperature. Okay, and in the beginning of their speech, they say that a picture is a key to understanding. Scientific breakthroughs often built upon the successful visualization of object invisible to the human eye. I think sometimes it's true, sometimes it's not true. But this is something we would like to do, in my laboratory too. Something people cannot see. I would like to see. Okay, so when the electrons is irradiated to the sample, in our case it's polymer samples, bulk polymer samples, not solution. Okay, then many things happen. Most of the electrons just go through. It's the transmitted electrons, and some scatters. Okay, and scatters in an elastically way or inelastically way. Elastically way, it comes in, then the electron doesn't lose any energy. It just scatter. Inelastically scattered electrons, it loses some energy, and then measuring how much energy that electron loses, from that you can do the elemental mapping, for example. Okay, that's underneath, and you have a secondary electrons or you have a backscattered electrons, and those are the two things that you often use for the SEM. So if you have experience to use the SEM, you either choose one of these. And then for the secondary electron, if you use secondary electrons, then what you observe is the surface undulation. And for the backscattering electrons, it contains elemental contrast. Also, you have a characteristic X-rays. Analyzing the characteristic X-rays, you also have elemental, information, like where the sulfurs are, where the other elements are in the sample. But I don't talk about the elemental mapping in my talk too, either. Okay, so when people talk about the microscope, they like to talk about. Please.
What are Auger electrons in the previous slide?
I'm sorry.
What are Auger electrons?
Sorry.
In the previous slide, the one on the right side, Auger electrons.
Auger electrons. how do you explain that? It's also related to the elements too, and the way the Auger electron comes up, it's a complicated thing, and it takes time. I'm sorry, I cannot explain that now. So resolution, okay. So you might know this equation. That's the resolution, and then is as a function of the converging angle and wavelengths, and it's called diffraction aberration limited resolution. And what that means is that you have an object here, and then either light or the electron comes in, and then it scatters in a different angle, and then if you have an infinitely large lens like this, then you can take up all the scattered lights or scattered electrons. Okay, then this object can be imaged at the image plane as a really good point. Okay, but in the real case, the size of the lens is limited. So part of the scattering can be captured, but some of the scattered electron or lights outside this lens, we cannot capture that. And these are the electrons or lights scattered at a very large angle, which means a small feature. Okay, so if we miss this small feature, then this point gets blurred, gets bigger. It's a blur here, and then that equation tells you, how much the converging angle, which is this angle, and the wavelengths, the combination of it, then how much the image is blurred. That's what that equation says. So for the light, the wavelength is something like a 500 nanometer for the blue light. Okay, and then this alpha is almost 1 if you have a very good lens. Then the resolution is something like a 200 something, maybe a little bit below than 300 nanometers. So that's a resolution for the light microscope. For the electrons, I will give you the number later on, but this alpha is much small. That means the quality of the lens is very bad. But the wavelength of this of the electrons is much smaller, on the order of 5 smaller than the light. Okay, so eventually the resolution of the electron microscope is much better. There's another thing we need to think about. That's the image blur. This is that equation is coming from the diffraction aberration, and this equation comes from the lens itself. Okay, and this blur is a function of the defocusing, focus, in focus, out of focus. That's called defocusing. If you have an under focus, if you have an over focus, the defocusing is large. If you are in focus, this is 0. Okay, that's the defocusing term, and these are the term related to the spherical aberration. So spherical aberration times alpha times cube, or maybe times 5. Okay. Typically, this spherical aberration is well controlled for the optical microscope, because optical microscope you have a convex lens, you have a convex lens, and convex lenses, and convex and what is that? concave, sorry, concave lens. So you can make these two lenses. A combination of these two lenses, you can actually make this spherical aberration constant very small. But for the electron microscope, it's a electromagnetic lens only. So it's a convex lens only. There's no convex lens for the electron microscope. So that the quality is very bad, so that this CS is very large. Okay? So there's two things we need to think about when we are talking about the resolution. Okay? But in 1995, a great scientist from Germany actually invented concave lens too for the electron microscope. So if you have lots of money, like $1 million, and then install this device into the electron microscope, then you have a very good lens. If you are not that rich, then you have to live with this concave convex lens only, right? Okay, and the wavelengths that I was talking about at the 100 kilovolts acceleration voltage, the wavelength is this small. So it's on the order of 5 smaller than the laser. Okay, and then if we want to see the atoms, the spacing between the atomic column is on the order of this much. Okay, so using this wavelengths, and then using a Bloch equation, and to calculate the converging angle, alpha, that would be 10 to the minus 2 radian for the 100 kilovolt electron microscope. And then, like I say, that the electron microscope lens is not good. This coefficient is something like 1 millimeter. And for the optical microscope, it's almost 0. Okay, and then even though the CS is large, we plug in here, and then this delta L, the blur, you can come up to a 0.1 nanometer. So that's why with the electron microscope you can observe the individual atoms. Okay. So the key point is that the short wavelengths, that's all. There are different types of electron microscope, and the SEM, scanning electron microscope, you probably know very well. And we have a converging electron beam, and then we scan it on the surface of the sample, and then from the surface, backscattered electrons or secondary electrons comes out, and you detect that. But the detection is above the sample, this side. Okay, you scan the beam, and then the detection is on this side. Transmission electron microscope uses not this converging beam, but a parallel beam. Okay, like this, and then we don't scan this beam. We just the beam just stay. And then focusing is in the sample, not on the sample, in the sample, and the detection is under the sample. Okay, the camera is here, under the sample. Okay, and like I say, we can achieve the atomic resolution because we have a very short wavelengths for the electrons, and then we can do the elemental analysis too. And the contrast generation is either absorption or phase contrast. That I will come back later. Okay, and then we also can take the diffraction pattern too. Under the lens, you have a back focal plane, and you have an imaging plane. Okay, at the back focal plane, it's a Fourier transform of the object, right? So if you insert the camera into this backscattered place, then instead of having the image, the object image, the real space, you have a diffraction. Okay, so that's why we can take diffractions. There's another one, scanning transmission electron microscope, we call STEM. This is a sort of a combination of these two. So in this case, we have, it's similar to the SEM. We converge the angle, and then we scan the sample. We scan the sample in the sample, okay? So converging beam and scanning inside sample, and detection is underneath, okay, not above, underneath. There's typically two types of the detector. One detector here to take the small angle scattering, and the another one, it's a round type, we say annular detector, like the donuts. That takes the scattered electron at the high angle. Okay, so there's two detectors. It can also have atomic resolution. We can do the elemental analysis too, and Z contrast I come back later. And then the important thing between this TM and the STEM is that TM, although I don't draw, there's a lenses underneath the sample, so you need to magnify it. So typically you have a four lenses underneath to magnify the image. Here for the STEM, there's no lenses, so the contrast purely comes to scattering. That's the difference. Yes.
Can you image biological samples with the beam is convergent? I imagine that it would damage the sample much more easily.
Yeah. I come back to the electron damage later on, but basically you can observe the biological sample too. Polymer sample and biological sample, it's almost similar in terms of the beam damage. So if you can observe the polymer sample, you can observe the biological sample too. Okay? Yes.
About the sample preparation, because for TEM and CM they'd be very different. And what about STM?
It's the same thing. For the TM, as you know, we typically normally use cryo microscope. It's like a cutter, the knife cutting the cheese. Okay, the thickness of the sample will be like 100 nanometer, 150 nanometer. So it's very thin sample, and the same sample can be used for the STEM too. And for the STEM, you don't have to use the microtome, right? You can just make the surface. That's all. Please.
Is the electron beam in TEM coherent?
Yeah, it's coherent. Yes. Otherwise, we cannot do this. Phase imaging. All right. So electron damage. There are 3-4 types of different beam damage. The first one is called radiation damage. Okay. There's the cleavage or recombination of bonds when we apply the electron beams, and this recombination or cleavage is done by active radicals generated in the material. Okay, so it's an ionization we call. Unfortunately, there's no solution for this. Okay, as long as you shine the electron beams, always ionization occurs, and there's nothing we can do about it. The second one is that we call Nocon damage. So when we put the electrons into the sample, and then the atom is kicked out, that's the Nocon damage. And to prevent or lowering that, we need to lower the acceleration voltage. So it's always a discussion that you're going to use 60 kilovolt TM, you're going to use 200 kilovolt TM. The answer is here. If you are talking about the electron beam damage, the lowering the acceleration voltage is better. Temperature rise. So you shine the electrons, then you vibrate the molecules, and then it's a phonon, right? and then it raises the temperature. And there's a solution for that. We can lower the temperature. So we can observe that we can put the image, and then we cool the sample to the cryogenic temperature, like minus 170. That's the thing you can do. The another thing is that secondary diffusion of defects, like cross-linking. It's related to the first one. Okay, when you irradiate the beam, and then the radical forms, and then sometimes radical attack the double bonds, for example, and then it takes a chemical reaction. Sometimes it's the cross-linking. So it's closely related to this. So, lowering sample temperature, it might help, okay, for this case. So from these damages, what you can learn is that lowering the acceleration voltage and lowering the sample temperature, that would.
What about the electrical charge accumulation?
It's a problem too, but it's not a damage. It's if you accumulate the statistics, then sample moves around. Instead of typically instead of damage the sample, the sample, because of statics, the sample just moves around. So in order to prevent that, you coat the carbon, for example, the thin layer of carbon on the top of the sample. Then you prevent that kind of thing. So, but this is always a discussion, I would say. Some people says lowering acceleration voltage is good, better than the high voltage. But some people says, no, the higher voltage is better. Because higher voltage electrons, it has a lot of larger energy, and they transmit without interacting the sample. So it does not damage the sample. There's a discussion like that. So, it depends. Actually, the answer is depends on the sample, and then it's true for the biological sample too. So the damage, beam damage is very complicated. So there's no universal solution. But the guideline is that, like I say, guideline is lowering acceleration voltage and cool the temperature, the sample temperature. That's the guideline. The thing we need to think about is that how about that? Then how to lower the beam damage? Only thing we can do is essentially is that we can lower the dose. We try to image try to have the image with the lowest amount of the electrons to the sample. Okay. So typically, when you do this, then the electron contrast becomes worse. If you put lots of electrons, and then of course the sample will be damaged. But if you take just one picture, then don't care about it, and then you put lots of electrons, then even though the contrast of the sample is small, you have a better image. But thinking about this beam damage, then you need to lower the dose. Then the contrast gets worse. So another thing we need to understand is that how the contrast is generated in the electron microscope, and then how to enhance the contrast. There are a couple of contrasts in the electron microscope. One is the scattering contrast. This is a graph of the scattering vector. This is the angle, essentially, and the intensity of the atomic scattering factor. So the different colors means different elements. Helium, carbon. Carbon is typical for the polymers or biological sample. It's here. Whereas gold is up here. So as you can see, the heavier the elements, the greater the electron beam scattering ability. That's general. Okay. So if we have a structure made of carbon and the gold, for example, then you have a lots of scattering contrast. Like this. So this is the sample. The gold is deposited on the carbon film, and it's a great contrast. Okay, TM. Yeah.
Why are the decays different shapes? Is this to do with electron shell at the energy level?
I'm sorry.
Why the
The decays is not the same.
Yeah, why is it?
I don't know. I don't know. Sorry. It's just a calculation, and then I don't know. No question about this TM picture. What I explain is different from the image here. Yeah, that's right. Carbon is brighter, and the gold is darker. And if you take this graph, then the scattering is smaller for the carbon and the large for the gold. Why is this? We need to go back to this cartoon, maybe. We need to go back to this cartoon, okay? That we are talking about the scattering, and scattering is go away for the TM, okay? So the gold, which has a very strong scatter, has a scattering in this way, and the rest, the remaining, is small. So underneath the camera, it gets darker, okay? So that's people call absorption contrast. Whereas for the stem, the image should be inverted because the gold scattered very strong towards the high angle, and the carbon also scatters, but it's a little bit. Okay, so if we take this stem, then and then place this annular detectors at the high angle, then the gold appears brighter, and then the contrast will be inverted compared to TM. So this part will be brighter. This part will be darker. So depending on which type of the mode of the electron microscope, the image is going to be different. So that's one thing you need to understand. Okay, this is TM. Okay, typically we blend the sample for two-component sample like polystyrene, polybutadiene, and then we have a structure like this, for example. But polystyrene, polybutadiene all consist of C and H. So in terms of element, it's almost the same. So there's no contrast under the TM. So that's why we use this staining technique. Like osmium tetroxide, ruthenium tetroxide, those are the two representative staining agents. And osmium tetroxide stains a double bond. So if we have a blend of the polybutadiene and the polystyrene, then the polybutadiene, which has a double bond, is selectively stained by osmium tetroxide, and then that appears to be darker under the TM. Okay, so that's the staining. You probably know that. There's a problem about this staining. Okay, when you stain, you expose the sample to the osmium tetroxide vapor, for example, and then how long you expose the sample to the vapor. If you do that too long, then the sample will be all black. If you just put the sample for a very short time, the staining may not be sufficient enough, so that we don't have enough contrast. So how long you're going to expose the sample to the vapor, it's important. It's empirical, actually. and then you do that staining in summer, and you do that staining in winter, it's a different thing. If you try to keep the sample for 5 minutes, in winter and in summer, it's a different staining, okay? And then the structure may change due to this staining too. And another problem is that, like I say, osmium tetroxide stains double bonds. That's common sense. Ruthenium tetroxide stains polystyrene, and they says that the reason is that the ruthenium oxide stains the benzene ring, but that's not being proved. So okay, butadiene, isoprene, styrene, you can stain with these two, but PMMA, no. So you have a PMMA and other other polymers that cannot be stained either, then there's nothing you can do about it. No staining will be done. That's another reason. And the last one is that if you stain the sample, then you essentially fix the structure. If you want to stretch the sample, for example, to see when you're stretching how this microphase separated structure changes or deforms, you cannot do that once you stain. So that's another reason, another problem. So the high contrast observation without staining is very important and it's very highly demanded. One way to solve this problem is that the phase contrast TM. Okay. So this is a graph. Again, this is the wave vector. So this is the angle essentially, and this is the function called contrast transfer function. Okay, and when the X-ray goes through, and then some electrons scatters, and then at the lens it bends and then goes to the focus. Okay, in this lens, the slight phase change occurs. Okay, and also the phase change occurs too here, but the length, the length how the electrons travel is different, so that there's a phase contrast. So the strength of the phase contrast is given this by this contrast transfer function, and this is sinusoidal function, and then in here it's over there. So sorry about this Japanese, but the first term is the defocusing term, and the second term is the spherical aberration term. So as you can see, defocusing and the spherical aberration changes the phase contrast. Okay, but the important thing is that this is sinusoidal. So the CTA, this contrast transfer function is normally this gray lines. So at the higher angle, corresponding to the small structure, we have a up and down. And then this 1 and -1 correspond to either dark or white or dark. Here at 0, it says there's no contrast. That's what the contrast transfer function means. Okay, so for the higher angle or smaller structure, there's many bumps. So if we set the optics right, then we can have either 1 or -1. Then we can image the image with the phase contrast. The structure of the polymer is typically on the order of 10 nanometer, for example, 20 nanometer. The angle, scattering angle corresponding this is somewhere here. So up to here, it's almost 0. So there's no way for the large structures to be imaged with this phase contrast. So what we do? What do we do? We insert carbon membrane at the back focal plane here. That changes the phase by 90 degree. So it changes the sign from the function from sine to cosine. Then the CTF is now becoming like this. Then we have a contrast, right? So actually, this cartoon is not quite right. We should have a little hole. That's much better. We should have a little hole so that this transmitted electron doesn't experience the phase change, whereas the scattered electrons here, the phase changes dramatically. Then we can have this situation. Okay. Yes. 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 The size is the if you have a phase separated structure, for example.
With the same size of the two phases.
Yeah.
So the scattering angle of the two compounds is the same. So this scale doesn't work anymore.
I'm not sure I understand this.
So there are no contrast because all is carbon and hydrogen, but the size is the same. So
Size of the sample, the structure of the sample. Yes.
the size of the two structure, the mean size of the two structure is equal. So the scattering angle of both components is the same. So the first length doesn't change, and then the second length, the carbon length.
I'm not sure. You're talking about two sizes, right? I'm not quite sure what the one size and the other size is.
I want to differentiate polystyrene and other element which has a low, which has a low contrast, and both are low contrast. We see nothing. We speak about enhancing contrast.
So in a conventional setup, there will be very small contrast, and then if we put this phase plate here in the optics, then the scattered electron beam has a phase change.
Yes, but for both compounds, the scattering of both compounds is equivalent. So the first length.
Oh, I see. I understand. Okay. If you say two components, so two components make some structures, like for example, like a spinodal decomposed structures. Then the spacing or periodicity. I'm talking about the periodicity, not the size of individual phases. Okay. Anyway, so yes.
So how this green bar, how does it rotate by pi by 2 phase?
It's made of a carbon, and then the thickness of the carbon is that matters. Yeah. And then this is the experimental result. 2 is result actually. This is a phase separated structure, lamellar structure of the polymers, and this is stained, osmium stained sample. You can see the lamellar structure here, and this is the unstained sample with the phase contrast. You can see the structure here, and this is another example. This is some sort of spherical domain or maybe particle or something, and under the conventional setup, it's nothing. But with the phase plate, we have a very good contrast. So that's one way to enhance the contrast. But the difficult thing about this phase contrast TM is that this phase plate, okay, like I say, phase plate has a hole in the middle where the transmitted electron goes through. So you need to finely tune the position of this phase plate so that the transmitted electrons just goes through. Okay, so it's a very fine tuning. And then this carbon plate is easily contaminated. So you need to exchange this phase plate, once maybe in 2 weeks. And you have to insert that and tune that every 2 weeks. That's pain. So the phase contrast is very effective, but it's not so common yet. There's another way to enhance the contrast is using stem. Okay, this is again the phase separated structure of the polymer brochopolymers and polystyrene and polyisoprene brochopolymers. This is stained sample, so that the black part is the polyisoprene part. Using stem and then imaging using this detector here, taking the small detector which collect the small angle scattered electrons, then that'll be like this. So you start to see some structure, and then you can change using this donuts type of structure of a detector, and by changing the camera length, you can change the scattering angle. Okay, this is inner angle, this is outer angle. So this is inner angle, and then this is outer angle. Okay, inner and outer. So these two has a detector at a different camera position. Okay. Anyway, you have a nice contrast, and then for this particular part, I show you a large scale TM picture, is a stem picture. You can see the lamellar structure very well. You may want to ask why. I come back to the reason why in my second lecture. So here, just please admit that using stem and changing the angle, scattering angle, you can change the contrast. That's another way to enhance contrast. Okay, so next one is electron tomography. I showed that earlier. And then in my laboratory, we use three-dimensional imaging for the precise characterization, structural characterization in these days. So one example is the brochopolymers, and as you know, depending on the ratio between the A and B blocks, you can have all sorts of different nanoscale, microphase separated structure. And between the lamella and the cylinder, there's a network structure called gyroid, as you probably know. And that was found in late 80s by Professor Thomas at MIT at that time, and then also Professor Hasegawa and Professor Hashimoto at the Kyoto University, in Japan. And this one is 86, one is 87. And the TM picture they showed is like this. So this is polystyrene, polyisoprene brochopolymer, and then stained again. So this black part is polyisoprene domain, and the white part is the polystyrene domain. Okay. So they come up to a model. This model, ordered bicontinuous double diamond structure. There's a minimal surface called diamond surface, and that divides the space 50-50. Okay, and then this picture is made by. So if this is the minimal surface, then we make a parallel surface in up and down. So you have two surfaces, and then you measure the volume fraction after this. And then the volume fraction of this network phase is something like a 33%, 34%, where that's a polymer fraction where we observe gyroid. Then we stop the traveling the parallel surface and fix the parallel surface. That's how we make this type of image, model. And it's a double structure. The blue one and the light blue one is the domain with the 34% volume fraction, but these two are not intersecting each other. They are independent. Okay, and so they come up with this OBDD structure, and later on, Professor Haruk reported that this structure is not OBDD, but OBDG. G stands for gyroid structure, the different type of a minimal surface. So for some time, there's a controversy whether this structure is diamond or a gyroid. Finally, I think this paper ends the discussion with very precise X-ray scattering analysis. This structure was sort of proven by gyroid structure. That's a story. But the point is that this is a picture that I saw for the first time as a TM image. When I joined Professor Hashimoto's laboratory, Professor Hasegawa showed this picture to me that was my undergraduate time. So that was 30 years ago. Okay, so this image stuck in my mind, and then although the structure is not the diamond but the gyroid, one of my small dream is that to visualize this structure into 3D. Okay. Again, the different techniques, but before I draw TM, this time it's a 3D TM. Okay, the TM comes somewhere here. It's a two-dimensional projection image, right? And TMT, so 3D image, 3D TM ends here, and that's because for the 3D TM, you need to have a thicker sample than the normal one. The normal TM, you probably need a thinner sample, like 100 nanometer thick or preferably thinner. But for the three-dimensional imaging, thinner sample to visualize into 3D, that's not very impressive, right? So we increase the thickness of the sample like 150. Then the transmittance is getting lower, and then like I explained later, we tilt the sample to do the imaging. So the cutting off is somewhere here. Okay. So the principle is here. Please.
For someone who does polymers, but on a much bigger scale, how do you prepare samples that are that thin?
How?
Sorry. How do you prepare samples that are like 100 nanometers thin, and does it not affect, I'm assuming if you change the preparation method,
Still, you can use the ultramicrotoming. You can still use the same technique. And then for in this instrument, you can set up the target thickness. You can set the target thickness like a 70 nanometer, or you can have it like 150 nanometer or 200 nanometers. So the same procedure. Okay. So the principle is here. So it's a CT. So you are the sample, and what this instrument does to you is that there's a combination of the X-ray, in this case X-ray source and the camera, and then this combination that rotates around the sample. Okay, and that means is that you are the sample, and then you take the instrument takes projections from different angles. That's the raw data. And then using the filtered backflow projection, I would like to explain a little bit later. You can reconstruct the cross section of the sample and then stack them together to make the three-dimensional, image of your sample. That's a very, very naive way to explain how we do the three-dimensional imaging. Okay. So some mathematics. No, it's not very mathematics, but you have a sample, and in this case, this is a two-dimensional sample, and then you shine the X-ray or shine the electrons through this sample, and then you take projections. Projection is P. Okay, and then the background is that your intensity here. I mean, intensity changes with the thickness of the sample in this way. That's the things you have to fulfill. And then projection can be right like this. Okay, so it's a simple way. And then x and y, x, y, and y, and coordinate is x and y, and then theta and r. That's a circular polar coordinates. You can change the coordinate into circular polar coordinates too. We take the Fourier, please.
Are you making scattering projections or imaging projections?
This is sort of absorption. Yeah. So the X-ray comes in and then travels in this sample long enough, then it's absorbed, and then the intensity is smaller. That's the idea. Okay, so we take the Fourier transform of this object, and that's the Fourier transform. And then again, you change the coordinates, and then the Fourier transform can be written like this. So there's nothing fancy. But you can compare this red part and with this. This is the previous slide, and this is P r theta. It's a projection. So that part is a projection. So it turns out that the Fourier transform of the object can be written like this, and then it's a projection, the Fourier transform of the projection. So what that means is that you shine the beam and then take projections, and then you take the Fourier transform of this projection, and that will be here. That's the idea. Okay, so like CT, you change the angle and then you take projection. That means you change the angles, and then you take projections from different way, and then take the Fourier transform, and then to fill the Fourier space like this. Then you can actually either rotate your sample or the machine rotates. Then you can fill the whole space, Fourier space. Then after that, you can do that is you can take the back Fourier transformation, bring the intensity and the phases from the Fourier space into real space. Then you can have the structure. That's the sort of mathematical background. So with the cartoon, on your right, on your left, this is your sample, and then take projections, and then you rotate the sample, and then take Fourier transform, and then for this geometry, you take the Fourier transform of this, and then put the intensity and phases here. And then what you can do is that you can rotate the sample and then fill in the Fourier space, and then you do the back Fourier projection, and then you have a structure. Okay, but this way, like 20 years ago, the machine power of the computer is low, and the memory is small. So rigorously you follow this is very difficult because your projected image has some bytes. I mean, takes up memories. You have to have lots of this data, and takes up lots of memory. You need a lot of memory, and then computing power. So it's not realistic to do this. So another way is this. So this is a Fourier the Fourier intensity and the back Fourier inverse Fourier transformation of the object function. Okay, and then what we do is that we change the qx qy. It's in a reciprocal space to a polar coordinate rho theta, and then we change the variables. Okay, we change this, then the equation will be like this. There's a Jacobian here. Okay, and then using these relations. Okay, so the projection of this hand is like this. Okay, so you understand this. This is theta plus pi is flipping, and then r gets minus r means, you know, if this is r and then it's flipping, it's going to be minus r. So it's the same thing. So you use this kind of a relationship and then make a calculation. Then finally it goes like this. So the object can be expressed like this. And then if you take a look at this equation very, very closely, then this part, I mean, from here to here, it's in a Fourier space. It's in a Fourier space. Okay, and there's a weighting function, but this is a Fourier transform in a Fourier space. So if you do this, then it goes back to the real space. In here we say Q, large Q, and then you plug that into here. Then it turns out that your structure is the summing up of the real image. And the real image is that, you know, this. So if we don't have this, then it's a projection. It's PR theta, if we don't have this. So essentially, what we can do is that we sum up the something very close to PR projection, and then we summing this up. But there's a difference here. But use the intensity, I mean Fourier intensity, and then we raise up to the higher angle. That's what it is. But what I get confused is that this one here. So this is the Fourier transform of the object, and then take the inverse Fourier transform. It's going to be okay. So this is only the d rho. We don't do d theta. So it's a function of the theta too, right? R and theta. So it's a projection. Anyway, what we can do is that in a real experiment, I mean the analysis, we have a structure like this, and then we have a projection, and then we back project the image, and then we tilt the sample and then take projection again, and then we back project according to the angle. We're gonna keep doing this. then eventually, you can reconstruct the original image. Yes. So this is a back projection. This is not filtered back projection because I don't take this filter weighting in this cartoon. So this is back projection. But as you can see, after taking projections and then you're going to stretch it, and then you keep doing this, then you realize this structure again. That's the back projection. And if you take these filters into the calculation, then it's getting much better, like this. So with the filter, it can reconstruct the original image, but without the filter, it's sort of blurred. I think I confused. So let me explain that maybe later on. But what I would like to stress is that we are doing this kind of thing. So what with this, with this filter back projection, you can just stretch it and then summing up. So in a computer, you don't need a very large computing power. That's the point. Anyway, so this is 1D than 2D. So if this is 2D, and then we do the same thing, it's going to be 3D. Okay, anyway, so summarizing, what we are doing is that we have a sample, and then we rotate the sample in the TM. Okay, take projections, and then using these projections, we can reconstruct the data. For doing this CT on a TM, especially in TM, there are a couple of problems. One is, again, the beam damage. This fire means that you keep on shining the electrons, then you eventually burn the sample. That's what this means. And the another problem is that what we call the missing wedge problem. And in this cartoon, we can freely rotate up to 90 degree or 360 degree. But inside the TM, there's a problem so that we cannot tilt the sample, rotate the sample up to a certain angle. That's another problem. And third problem is that's a misalignment of the tilting axis. In this cartoon, in your sample, the axis is right in the middle, and then as you rotate, your sample is rotating very nicely. But in reality, in the TM, because this is your sample holder, and then this is the blow up of the sample holder, tip of the sample holder, and this whole thing goes into the instrument like this. Okay, and then inside this instrument, there's a carton like this, and then this is the tip of the sample holder, and this is objective lens. Okay, so there's a goniometer. And there's a goniometer, and then you tilt the sample using the goniometer, and then in the goniometer you have your sample holder in. Okay, so the how we tilt the sample is using this goniometer. So the important thing is that the sample and the center of the goniometer should be the sample should be on this center. Okay, you know what I mean? So that means if this is the tip of the sample holder, you have a sample holder sticking in, and then you take a look at the sample holder from this side, then it's like this. And then your sample is on not here on this is the center of the goniometer, not here but somewhere here. Then you tilt the sample, and then your sample moves like this. So the sample is moving like this. So the focusing is messed up, and the projection is going away. So eventually, you know, the image is going out of the scope. That's the problem. Yes. Like this. This is your holder, and then your sample is on the holder, and then you stick the whole thing into the sample, into the instrument, and then you tilt like this. And then this is a picture you are taking a look from this side. So this way. Okay. So what you need is that you need to move the sample holder so that your sample is on the tilt axis. That's you need to do. Then your sample rotates along the tilt axis. So it's a very important thing when you do electron tomography. And there's a problem associated with the TM, but I think I spend time, right? 2 minutes or so. Just 2 minutes. I can just tell the audience what's the problem, what's the essence of the problem is. Okay. So again, we have a holder, and then we are sticking the holder into this. Okay. And then again, we take a look at the holder from this side. So this side. Okay. So there's your objective lens, and then your holder is like this, and then you tilt like that. So as you tilt too much, then it physically hit the objective lens. Okay. In order to prevent that, you need to have a lot of space. But if you have a lot of space, then you lose resolution. Typically, this space for the typical electron microscope is 2 millimeters or so. So for the electron tomography, you have a special type of objective lens which has a wide gap. But this could happen. And the another problem is the sample. Like I say, sample is microtomed. It's a thin sample, and then like this, okay. And then you have an electron going through, and then take image. You tilt the sample. Then the original thickness is of, let's say, 100 nanometer. And as you tilt the sample up to 60 degrees, the effective thickness that the electron has to go through is going to be double. If you tilt up to 70 degrees, it's going to be triple. So although the initial thickness is 100 nanometer, 60 degrees it's going to be 200 nanometer, and then 300 nanometer. As your thickness gets thicker and thicker, your image gets worse and worse. Those are the two limitations where we cannot tilt the sample up to 90 degrees. That causes a lot of problem. But I think I used my time. So I finished my first lecture here, and then I start the next lecture from here. And then try to go much more speedy next time, and then talk about the applications. Okay, thank you very much.